You know what, hold on. Before we get into this, let's do this. We're looking at here is graphical momentum. That is momentum in two dimensions. And we're sitting here with 101010 looking at kind of an intro to this, seeing how it kind of goes. But basically, everything we've been doing thus far with the conservation momentum, that's our super long equation, has been in one dimension. It's just been along a line. So like stuff's moving left or right, and then stuff moves the other way, and they hit, and then ta-da, we did it. But that's not how things work in real life. Like, you know, if you've ever played a game of pool, which I am just the worst at, so bad. You know, you've got this like pool table here, relatively speaking, and you know you've got like, yeah, this is a pool ball, and you're like, oh look, I'm doing it. I can play pool so well. And I'm like, I can't. You know, if you strike a ball like this, and it goes over here, and it hits these, and then this one's like, oh, I'm so fancy, and it goes in, and this one's like, I'm not, and it bounces around and does that last shape didn't make any sense, but you get the idea, right? Like these pool balls, they bounce around, and then it's like, I'm doing it, and then that's an 8-row bounce because I'm the greatest. But you get the idea. We're not playing just left and right anymore. We're playing in like 2D space, which things get weirder if you think about 3D space. Oh boy. But we're not. We're sticking to 2D because if you can do this in 2 dimensionals, then sending it out to 3 dimensions isn't really any extra work. It's just something else you do. Okay? But because these are in 2D spaces, what we could do to something like this is, and, you know, and you'll see this if you do this kind of in college. We're going to kind of ignore it for right now. But what you could do if you have an object kind of move out and then it ricochets away and then this object moves like that, is you could pull out SOHCAHTOA, start building a bunch of triangles and being like, oh yes, the triangles, I love the triangles. And that's totally fine. You're totally cool to do that to an extent. But sometimes we don't actually have enough information to use SOHCAHTOA. SOHCAHTOA leave us in the dark, which is a bit of an issue. But what we can do sometimes is if we have initial momentums, and I say initial momentums of the system, so kind of both objects there, then what we can do is we can add those initial momentums together. So pretend for a second, you know, if we're looking at the billiard balls, here's like the cue ball, and then here's, you know, whatever this is. I think it's like 3. If these strike and this number 3 ball, oops, I didn't want to do that, goes out like this, and this billiard ball, you know, kind of rolls down like that, then what we can do is we can say, hey, if this was the one that was moving and this was stationary, let's look at these initial conditions and add them together. And when we're adding them together, we're adding their initial momentums together. That's what we care about. So if we do that, we would see for this case that we have a vector just kind of pointing to the right by some amount. We don't know how quickly these 2 momentums are going. So we know this value, we're given it through some measure, we know the mass of the balls, we know how fast we hit them, whatever. But these momentums at the end are completely unknown. And because of that, the only thing we can do is we can say, well, I know that this number 3 ball, as it's going out, the blue one, it's going out at this angle. I don't actually know how long its momentum vector is, because remember, momentum is a vector. It has some length. It has to end with an arrow somewhere. I just know it's along that line because I could watch the ball go like that. On the flip side of things, we also know that the cue ball, it's going down like this by some amount. But once again, I don't know how far it goes. It just goes. But what we do know is that if we added these values up via the head-tail method, that initial momentum we had has to equal the final momentum of the 3 ball plus the final momentum of the cue ball. There we go. So what we can do here is, if we remember back to unit 3 or 4 when we talked about adding vectors with the head-tail method, this addition sign is the head-tail method. So what I can kind of simulate is I can pretend for a second that I take this vector of the billiard ball and I can slide it up along the 3 balls vector. So it's kind of going up like this. And when I do that, I see, hey, I'm not at this proper final location yet. That's where I'm trying to end up. So I need to keep sliding along the 3. When I keep sliding, I'm not there yet. But when I get right here, ding, I've arrived. And what this means is that all of... I actually know the values of the billiard ball. It means that the 3 ball actually has to end here. This is its vector. And the rest of this is just nonsense. It can just go away and just erase it out. But what we essentially have here is this is the initial momentum in orange equaling the other 2 momentums added together. And it's kind of a neat way to do that. You use for this to kind of get these final momentums. You'll end up using a ruler. You'll end up using a protractor. Okay, so those are kind of important. Don't break them. But that's what's going on here. We're kind of setting this up like that. And even though we don't know what these values could be, because we could measure and scale these values, we can get somewhere with that. So hopefully that was just kind of a quick overview of what we've done in class regarding graphical momentum in the 2D. But that's what's going on here. We're just plotting things and graphing them back so that the initials once again equal the finals, and there's nothing crazy there. Okay. So I hope that kind of helped. Hope it was a little bit of head start, or if you missed class, you can kind of catch up with that. So there you go. There's also